Chemistry, Paper 1, Foundation, May 2023. Okay, so question 1 is a chromatography question, and we've been given this chromatogram showing we've got these 4 different inks and they've separated into different dots. And first thing we had to do was say which ink contained a single dye. So we're looking for the ink that's only got 1 dot, and that is going to be Z. Which ink contains the greatest number of dyes? So we're looking for the one that's got the most dots. So that's got 3, that's got 2, that one's got 4. So therefore it must be C. Then we had to calculate the RF value for this dye. And we've been given the formula for working out. So RF is distance moved by the dye divided by distance moved by the solvent front. We've been told that the dye had moved 3.6 centimetres and the solvent front had moved 9.2 centimetres. So our RF equals 3.6 divided by 9.2, giving us an answer of 0.3913, but we had to give our answer to 2 decimal places, so we've got to round this to 0.39. So you're going to get 1 mark for doing that calculation, and then 1 mark for your answer rounded to 2 decimal places. Right, we've got a graph here which shows the temperature of something over a period of time. So we've got a liquid here that is being heated up, and then it gets to this period here where it's changing state. So all the particles are gaining energy to break any attractions between the particles involved. Once they have all separated from each other and all those attractions have been broken, we can then continue to heat up the gas. So we have to give the name of the change when a liquid becomes a gas, evaporation or boiling. And then we had to use the diagram to give the temperature of the substance at 4 minutes. So let's have a look on here. So we're reading up from here, and it's at this point, and then we can read across on the line, and we can see there that it's 56 minutes. We had to calculate the temperature rise of the substance from A to D. So we know that it's 25 degrees at this point here at A, and we're looking at how far it has got to get to D. And if we read across here, we can see that we're at 75 at this point here, so it's just there, so that's 75 there. So it's gone from 25 to 75. So the easiest way to work that out is just to take one from the other, and that gives us an answer of 50 degrees C for question 1. Okay, question 2. We've got our gold purity here, and we've got a graph that shows how the percentage of gold is related to the purity of the gold, and that's measured in carats. And we have to state the relationship between the percentage of gold and the number of carats. So what that means is, as the purity of the gold goes up, how does that affect the percentage of gold that's in there? And we can see in here that as you increase the purity of the gold, the greater the percentage of the gold. So I would write, the higher the purity, the higher the percentage of gold. And then here we've got these lovely diagrams showing some pure gold and an alloy of gold. We had to explain why alloys of gold are stronger than pure gold. So, mark number 1. In pure gold, all of the atoms are the same size. Or you could say the opposite, in the alloy of gold, the atoms are different sizes. So there's your first mark. Number 2, in pure gold, the atoms are in layers. Okay, or again, you could say in the alloy, they're not in layers. Mark 3, in pure gold, the layers can slide over each other, but in the alloy they can't, because you've got all these different shapes and different sizes in there, so therefore it's harder to slide over, and therefore the alloy is stronger. Explain one property of alloys of gold other than their strength that makes them suitable for use in jewellery. So you could have any of the following combinations. So explain means you've got to say something and then say why. So normally it's a thing and then because. So for example, I would say gold is unreactive. Why does that make it a good property? Because the metal will not react with, let's say, skin or oxygen. Or you could say gold is malleable. That means it can be shaped. Means it can be shaped. Or for your pair again, you could say gold is shiny, which means it is attractive. So on this question, you get 1 mark for stating something about it and 1 mark for explaining. Okay, question 3. Here we have a nice bit of electrolysis, everyone's favourite topic. What statement describes what happens during electrolysis? Or remember that in electrolysis we are using electricity to break things down. So therefore we're looking at which one talks about breaking down, and it's here. But it must be ionic things, ionic compounds that are decomposed. Atoms don't decompose. Then we had some labelling to do. So we had to complete the labelling of the diagram. So the negative electrode is the cathode. That makes the positive one the anode, and the liquid is the electrolyte. If you got all 3 correct, you got 2 marks. If you got 1 or 2 correct, you got 1 mark. Okay, so we've got the product of electrolysis shown in figure 5 are solid X and gas Y. Draw 1 straight line from each product to its name. So you've got solid X here, you can draw to 1 thing. And solid X is going to be copper. So remember, here we have got some copper chloride solution being electrolyzed. And at this point here, we've got copper ions going from the solution onto here, and we're coating the electrode in nice fresh copper. And then gas Y, well, we've got copper chloride, which means that our gas must be chlorine. So 2 marks there. It's repeated using solid copper chloride instead of copper chloride solution. Remember, solution means it's been dissolved in water. Why does nothing happen and no products are formed? So mark 1, no current will flow. And the reason, because the ions can't move. Okay, question 4. So we've got some stuff here about iron and steel, and then we talking about some steels will corrode when they're in damp air. What gas in the air is needed for corrosion to occur? Hopefully we all know that that is oxygen. And then we had to say what type of reaction happens when the iron in the steel corrodes. So it's reacting with oxygen. So our answer is going to be it has been neutralized. And then we have a bit of maths for us here. So we have got the formula of iron chloride, and we have to calculate the relative formula mass of this iron chloride. And we've been given the relative atomic masses. Now in our formula here, we've got Fe, and we've only got one of those because there's no number after the Fe. And we've got chlorine, and there's 3 chlorines because there's a little 3 after the Cl. So to work out our relative formula mass, we need to do 56, because that's the mass of iron, and then we've got 3 lots of chlorine, so plus 35.5, plus 35.5, plus 35.5, and that gives us a relative formula mass of 162.5. Remember, you are allowed a calculator in the exam. You should be using a calculator to do these calculations. Okay, so here we've got some different type of steel, which shows how much of different elements there are, and we've got another steel here. So this one's got a low resistance to corrosion, so it's very easily corroded. This one's got a high resistance to corrosion, so it doesn't corrode very easily. This sort of thing might be stainless steel or something like that. Using figure 6, state which non-metal is in both types of steel, and you've got 5 to choose from. So if you're not sure, you can always go through the periodic table, but the answer that we wanted here is carbon. Carbon is not a metal. And then we had to say which metal is added to steel to increase its resistance to corrosion. Well, let's have a look at this. So in the one which has got low resistance to corrosion, it's got iron and carbon and manganese and nickel. In the high resistance to corrosion, it's got all 4 of those, but it's also got some chromium. So the answer must be chromium. Give one other way that corrosion of steel can be prevented. There's loads of possible answers here. We had to explain why it works as well. Okay, so options. Paint it, grease it, coat with plastic, and then the reason, because it stops oxygen touching the metal. Or galvanizing, that means coating it with zinc, because stops oxygen touching the iron. Or sacrificial protection, because the more reactive metal corrodes instead. So any of those 3 options there. So you've got a thing you would do, 1 mark, and why that would work for your 2nd mark. Okay, students given 2 nails of the same size but made of different types of steel, and they're given 2 boiling tubes and some distilled water. Devise, that means come up with or work out how to do it, an experiment to show which nail corrodes more quickly. So, what I would do is a quick diagram. Put some distilled water in some boiling tubes. Nail A, nail B. Right, got a nice mark here. Mark number 2, leave for a few days. Mark 3, see which one forms the most rust for your third mark. So nice simple stuff. I think the thing to learn here is what devise means. Question 5. Okay, so we have been given some information here. Let's read through this together. When lead nitrate solution, that means dissolved in water, and potassium chloride solution are mixed, potassium nitrate and a precipitate, that means solid stuff, of lead chloride are formed. You know, to complete the word equation for this reaction. So it's telling us that lead nitrate has been mixed with potassium chloride. So we need to have potassium chloride here. And then we have got potassium nitrate being formed with our lead chloride. So potassium nitrate just there. And you get 1 mark if you got both of those correct. Then, which hazard symbol should be on a container of lead nitrate? Lead substances are really poisonous, so it would be that one, which means toxic. Okay, students put 5 centimetres cubed of potassium carbonate solution into a test tube and added 2 centimetres cubed of calcium nitrate solution. A precipitate, that means a layer of solid at the bottom, and was allowed to settle as shown in figure 7. So there's our precipitate, here's our solution, here's our test tube, and the height of the precipitate has been measured here with a ruler. Okay, so 1 mark for naming something you'd use to find the volume of the potassium carbonate solution, a measuring cylinder. You could also have allowed a pipette or a burette, like our titration work. Okay. Here's some results from the experiment. Experiment 1, you got 2.4 centimetres of precipitate and so on. Use the data in figure 8 to calculate the mean height of the precipitate. Okay, so all we've got to do is add them together and divide by 3. So 2.4 plus 2.7 plus 2.4 gives us an answer of 7.5. 7.5 divided by 3 gives us an answer of 2.5 centimetres for this. Okay, how could you get a pure dry sample of precipitate from the mixture in the test tube? 1, filter it. So filter it, the liquid will go through the filter paper and it will collect the solid. Mark number 2, wash or rinse the solid with distilled water. I've put distilled in brackets because that's optional. You would get the mark just for water. Mark number 3, leave it to dry. Would be enough there. You would normally do it in an oven. Okay. The student investigated whether increasing the volume of calcium nitrate solution increased the height of the precipitate formed. They repeated it using the original volumes of calcium nitrate. And you'd think of one variable that should be controlled. That means kept the same. And you could have any of the following things. You could have the volume or the concentration of potassium carbonate. You could have the concentration of the calcium nitrate or the time for settling. Just having time on its own would not give you the mark there. Okay, so question 6 then. So one physical property, so that's not to do with chemistry, just a physical thing. Any of the following: shiny, high melting point, good electrical conductor. All those sorts of things would be really good for that. So I'm just going to adjust my camera slightly. I think I might have knocked it. Okay, next up then, which element in the same group of the periodic table as magnesium? Remember that the groups are the columns, so that's the up and down. So you have to look at your periodic table to do that, and the answer that you would find is that it's strontium. That's the only one that's in the same column. Magnesium atoms have got 12 electrons. Complete the electronic configuration of a magnesium atom. Well, let's just sketch it out in this space here. So we've got magnesium here. It's going to have 2 in the first shell. 1, 2, 3, 4, 5, 6, 7, 8. So we've used 10 so far out of our 12. So we're going to have 2 more. So therefore that must be a 2 that goes on the line there. Then it tells us the electronic configuration of a chlorine atom is 287. Explain how the electronic configuration of chlorine is linked to its period in the periodic table. Remember that periods are the rows in the periodic table. So, chlorine has 3 shells. It's got 3 numbers, so first shell, second shell, third shell. Chlorine is in period 3. So it's always got the same number of shells as the period number. And then here's some maths for us. So we've got 1.2 grams of magnesium is reacting completely, so that means all of it's used up, with 3.55 grams of chlorine to form magnesium chloride. Calculate the empirical formula of the magnesium chloride, but that's the simplest ratio. And these calculations come up every single year. We need to make sure we can do them. So let's work our way through it. I always start by writing the names of the 2 in here. And then we also want to have our mass and our relative masses here. So magnesium has got a mass of 1.2 grams. And chlorine's got a mass of 3.55 grams. Then we've got our relative masses. Chlorine is 24, chlorine is 35.5. You might be spotting a pattern here already. We can then turn this into a mole calculation by turning this into a divide sum. And if you do that, you get an answer of 0.05 and an answer of 0.1. What you have to do here is then work out the whole number ratio of this to this. And the easiest way to do that is to have a look at your 2 numbers and work out which is the smallest number. And in this situation, it's 0.05. And then we're going to take that really small number and divide both of these by that small number. So 0.05 divided by 0.05, that's going to be 1. And 0.1 divided by 0.05 is 2. Now we've got a whole number ratio. And that whole number ratio tells me that I'm going to have 1 magnesium atom and 2 chlorine atoms. So we're going to end up with a formula of Mg1, because there's 1 of it, Cl2, because there's 2 of it. So our empirical formula, MgCl2. In terms of how you get your marks, those 2 sets of working there gives you 1 mark. Working out your formula is your second mark, your ratio is your second mark, and then your formula is your third mark. Okay, here's a nice 4-mark question then. So we have got our 2 ions here for sodium chloride in its ionic bonding, and here we've got hydrogen chloride, which is covalent bonding. We have to describe the differences between an ionic bond and a covalent bond. So I would suggest separating your answers out. So let's start with ionic bonds. And we have got an electrostatic force between oppositely charged ions. What does that mean? Well, that means that you've got a positive charge and a negative charge and they attract each other. So you would get 2 marks for that statement. If you only said it was between a non-metal and a metal, you would get 1 mark for that. And then for covalent is a shared pair of electrons. If you just said shared electrons, you'd get 1 mark. It's the pair that gives you your second mark there. So 2 marks for that sentence, 2 marks for that sentence. Question 7. Keep knocking my camera, I'm so sorry. Okay. So we're to say which of these elements, which is often present in fertilizers, is not present in this fertilizer. So remember, fertilizers have got nitrogen, phosphorus, and potassium in them. Which one's not present in this fertilizer here? Our answer is going to be phosphorus. How do we know that? Because there's 0% phosphorus oxide in there. Ammonium nitrate is prepared for use in fertilizers by neutralizing ammonia with an acid. Which acid will react with ammonia to make ammonium nitrate? It's going to be nitric acid. Why do farmers spread fertilizers on their fields? So crops grow faster. Hopefully we all know that. You could also say it provides nutrients for plants. Ammonium sulfate is a fertilizer produced in large-scale industry. In this process, ammonia reacts with sulfuric acid. Write the word equation for the reaction between ammonia and sulfuric acid. So we know that it's these two reacting together. So let's start with that. Ammonia plus sulfuric acid. And it tells us that we're making ammonium sulfate. And there's nothing else given to us in the question, so that must be it. So you get 1 mark for those two on the left, 1 mark for that one on the right. All right then. Ammonium sulfate can be made in the laboratory by titrating ammonia solution with dilute sulfuric acid. But that's when we had the long tube and we ran it down into the conical flask. In fact, here's a burette here, and it went into the conical flask like that, and we swirled this to make the reaction happen. We had to say one disadvantage of using this laboratory method to produce ammonium sulfate as a fertilizer compared with an industrial method. So industrial just means on a very, very large scale. So the one disadvantage is it would only make a small quantity of ammonium sulfate. Or you could say it needs to be on a much larger scale in industry. Okay, so we have got our ammonium sulfate crystals made using ammonia solution and dilute sulfuric acid. We've worked out how much ammonia solution is done by titration. We've neutralized 25 centimeters cubed of dilute sulfuric acid, and we've used an indicator. And the results are used to make a solution. So prepare a solution just means to make a solution of ammonium sulfate, and we can make our pure dry crystals from this. 6 marks to write a detailed method to make ammonium sulfate crystals. If you are looking up how to do this, the method is often called preparing a soluble salt, because the thing you're making dissolves in water. So there's loads of steps that you can put into here. I'm going to go through lots of these to go through the different sections. So first of all, you could use a pipette to measure 25 centimeters cubed of sulfuric acid. Place in a conical flask. Add indicator, probably going to be methyl orange. Use a white tile under the flask, then you can see the colour change more easily. Excuse me. Fill the burette, remember that's the burette here, with ammonia solution. Add the ammonia, swirling the flask. Stop when the indicator changes colour. And then once you've done that, because we want to make pure crystals, we then repeat without the indicator using the volume that we worked out just now. So there's the first part of our experiment. That tells us how much of each thing that we need to do. To then do the second part then, pour the solution into an evaporating dish. Heat it with a Bunsen until crystals start forming. Leave to cool and collect the crystals. So there's all the stuff that we could have written. Let's have a look at how the marks are awarded. So for 6 marks, you had to give a detailed description of the titration. That's using the burette and pouring it into the conical flask, and then a little bit of detail about crystallization, or a really detailed description about crystallization and a little bit of detail about a titration. So I'm just going to leave this on the screen for you so you can have a look at how the marks are awarded for the lower marks as well. You really must be answering these questions. You cannot afford to leave them blank. So please do not leave them blank in the future if you left this one blank for this question. It's really not acceptable. Question 8. So we've got some powdered calcium hydroxide, and we did this one, we added the powdered hydroxide and it stayed acidic for ages and ages and ages, and then all of a sudden it changed its pH. And that's the experiment that we did on that one. So what should we do after step 2 to make sure that it is complete? You should stir or swirl or shake the container to make sure it's finished. Then we have our word equation. So remember, we have base plus acid makes water and salt, Bohr's. So we're going to have water, and then the salt that we're going to get is taken from the calcium and the chloric bit. So calcium chloride. Which row in this table shows the state symbols for powdered, or powders are solids, so it's going to have to be one of these two, and dilute hydrochloric, that means it's mixed with water, so therefore it must be that one there. AQ is for aqueous, which means mixed with water. And here's a graph of the results that we saw. So it stays very, very acidic and then suddenly neutralizes and becomes alkaline. And you had to give the pH of the acid at the start. Well, it's exactly in between 0 and 2, so it's pH 1. And you had to give the mass of calcium hydroxide required to make it neutral, so it's at this point. So if we follow down here, we have got 0.74 grams there. Why does the pH start at a low value and end at a high value? So remember, starting off with the solution is acidic, or it has a high concentration of H plus ions. So that's why it starts off low. We then have neutralization. So that's when the acid reacts with the alkali. And here's the reaction that we're talking about. The H plus we just mentioned reacts with hydroxide ions to make water. And then your third mark is for the number of H plus ions has decreased. State what should be used to measure the pH of the mixture in this experiment. You could have a pH probe, pH paper, or universal indicator. No other indicators would tell you the pH, they would just tell you if it's an acid or an alkali. And then the calcium hydroxide is corrosive to the eyes and an irritant to skin. State one safety precaution that could be taken. Wear eye protection. So there's question 8. Question 9 has a reactivity series. So this one's the most reactive, this one's the least reactive. Which one of these metals will react when added to cold water? So it's going to be the one nearest the top. So that is going to be calcium. Okay. The student has added some metal to different types of metal to dilute hydrochloric acid, and they've recorded their observations for zinc. So some bubbles produced at a steady rate and it gets slightly warm, and copper does absolutely nothing, so they've written no reaction. What do we think would happen if you reacted with magnesium? So it's more reactive than zinc, so lots of bubbles, or you could say the tube gets hot. So 1 mark for either of those. For the second mark, there'd be a few bubbles, or bubbles are made slowly, or you could say the tube doesn't feel warm. Test to show the gas is hydrogen. We should all be getting full marks on this. We have a lit splint, put it into the tube, squeaky pop, 2 marks. All right, balancing the equation then. So we're told the magnesium, there it is, reacts with hydrochloric acid, there it is, making magnesium chloride, there it is, and hydrogen. Remember that hydrogen is a diatomic gas, so that means it's got 2 atoms in the formula. and then we just had to balance it all out. So if we have a look at this, we've got one H here and two H's here, so we need to have another HCl, and now we're balanced. We've got two chlorines, so we can just put a 2 in there. So you get 1 mark for the H2, 1 mark for the 2. And then we have our 6-mark question. So we've got 3 common methods of obtaining metals from the Earth's crust. We can mine it, we can mine the metal ore and heat it with carbon, we can mine the metal ore and electrolyse the molten compound. And the method that we use is linked to where it is in the reactivity series. Aluminium, gold, iron and silver are some commonly used metals. And you had to use the reactivity series on the previous page. Let me just try and find a piece of paper with that reactivity series on it. So using this reactivity series to explain the method used to obtain, that means to get, each of these 4 metals. So we know that our metals that we've got here, let's write our own one here. So aluminium is the most reactive, then iron, then silver, then gold. Okay, so there's our 4 things there. And let's just write about all 4 of those metals. So aluminium, I'm going to use the symbols because it's a little bit less to write. How's it extracted? It's extracted by electrolysis. And the reason is because it's more reactive than carbon. Remember, if it's less reactive than carbon, then we can mix carbon with the ore, and the carbon will displace the oxygen, leaving just the ore, the metal on its own. We can say that aluminium is reduced, and we can say that electrolysis is expensive. Then we can talk about iron, symbol Fe. We heat it with carbon. Let's write the equation out quickly. So we'd have iron oxide plus carbon goes to iron plus carbon dioxide. So what happens here, because the carbon's more reactive than the iron, it takes the oxygen to make carbon dioxide and leaves the iron on its own, which is useful for us if we're trying to get iron. We can say that the iron is reduced, and we can say this is cheaper than electrolysis. Okay, and then silver and gold, symbol for the AU there, are very, very similar. So they are found uncombined, that means on their own, in the Earth's crust, because they are unreactive. Okay, how are you given your marks? Let's have a look at the mark scheme here. So you can see, to get 6 marks, you've got to identify a method to extract at least 2 metals and reasons why. Okay, or give the method for 3 of them and explain 1 of them. So if you've actually answered the question properly, you will easily have given those. If you've only talked about 1 metal, then you end up with fewer marks than that. But we're looking at this information here. This is what we should be doing. So I'll leave that for you to pause and make some notes. Question 10. So here we've got the production of sulfuric acid in industry, and we're told that it's done by reacting copper sulfide and oxygen with copper and sulfur dioxide, SO2. And we had to calculate the atom economy for the production of sulfur dioxide. Remember, atom economy is a measure of how many atoms in the products are actually useful. So we're trying to make sulfur dioxide here. So the first thing that we have to do is to calculate the total mass of everything that is on the right-hand side. In fact, you can do either of the sides, but the right-hand side in this situation is easier. So we're going to first of all calculate our total mass. And we've got 2 lots of copper. So that is 63.5 and 63.5. And we're adding that to SO2. So if you look on here, that's 64. And that gives us an answer of 191. So there's our first mark here. Our next mark we need to do then is to work out how much of that is useful. So this is a percentage calculation, and the useful stuff is the 64 of the sulfur dioxide. So it's going to be 64 divided by 191 multiplied by 100, and that is going to give us our next mark here. So 2 marks for that. We end up with an answer of 33.507%, mark number 3. But notice the question says to 2 significant figures. So we have to then round this. So 33.5 becomes 34% for our 4th mark here. Then we've got some vanadium oxide, V2O5, and it says, based on the position of the vanadium in the periodic table, which row shows the most likely melting point of vanadium and the colour of vanadium oxide? Now remember, we know 2 things about transition metals. First of all, they make coloured compounds. So vanadium oxide, that is a coloured compound. It's a compound here, so it must be one of the orange ones. And then we know that metals have high melting points, so we're looking at D here for our answer. Okay, here we've got a reaction showing how sulfuric acid is made. So sulfur trioxide reacts with water to make sulfuric acid, and we have to calculate the maximum mass of sulfuric acid that can be produced from 400 tonnes of sulfur trioxide. So this is quite a hard one to do. So let's have a look at how we're going to approach this. We know we've got 400 tonnes. Now we can just ignore the units here because the grams would be equivalent. So just 400 is absolutely fine to use. And we need to find out how many moles of sulfur trioxide we have got in 400 tonnes. So remember, moles equals mass divided by Mr. So let's work out our moles here. It's going to be 400 divided by, well, they've given us the MR of sulfur trioxide divided by 80, and that gives us 5 moles. So we've got 5 moles of sulfur trioxide. Let's have a look at our equation here. So we know from here that it's a 1-to-1 reaction because you've got the same number in front of sulfur trioxide as you have sulfuric acid. So then we're going to use this rearranged. We need to find the mass. So mass equals Mr. moles. So our mass for our sulfuric acid is going to be 98 multiplied by the number of moles, which gives us 490 tonnes as our answer. Okay, on to the next one then. We've got to calculate the percentage yield of the sulfuric acid. Remember that percentage yield is the actual yield divided by the theoretical yield times by 100. So we've got our actual yield here is 672. We should get 700. Multiply all of that by 100, and that gives an answer of 96%. And then finally, 2 reasons why the percentage yield is less than 100%. And there's 3 possible ways you can get the marks here. Number 1, it was an incomplete reaction. Maybe Some of the stuff just didn't end up reacting. It was just, I don't know, covered with some other things, didn't get exposed to the water or something like that. Number 2, we lost some of the substances. Maybe it was stuck to the side of the container, or maybe it puffed out when the reaction happened, a little bit was lost that way. Something like that might have happened, that we've lost some. And our third one is unwanted side reactions. Maybe some of the sulfur trioxide reacted with some oxygen in the air instead and made something completely different. We don't know exactly what might have gone on. And there's the end of the paper. Well done.